Episode of the podcast. I'm
Sorry
Spectre
about
with
that,
me.
Spectre. Start over again. The
Start
transition
over?
to the main screen didn't quite happen on time.
Okay, no worries. Hello everyone. Welcome to the binary episode of the podcast. I'm Spectre with me is Z. And this is our first binary episode of 2023. And to usher in the new year, we have a new Spot the Vuln challenge as well, which I'll let Z cover the solution for. So go ahead, Z.
Yeah, so this week's Spot the Vuln, based off of one of the topics that we covered on last episode, which was the Python prototype pollution topic. What you got in the code here is you've got just a random class called record. Doesn't actually do anything in this case. It's just kind of a stand-in for some arbitrary class. You've got this merge here, which is basically just taking things from one object. Later on, that gets used to merge all of the objects from the argument to JSON request coming in. Data field in there, everything in there gets merged into the um, attributes of record. So I can just go and apply whatever's there if it matches. It effectively, the vulnerability here is similar to prototype pollution, or you could think of it along the lines of like a mass assignment. The primitive that you're getting is that in that merge action, you're basically able to set the value of any attribute or like nested attribute of this Python object or Python class. So where they take this attack for the actual uh, in the original paper or article on this, where they take that is starting to look at some of the internal representations kind of inside of these Python objects, like Python underscore underscore, the dunder methods they're called. They're special methods like class or base, and you can kind of navigate your way through the different classes and actually add attributes to a class that will then be reflected when they get used. You can also access things like if you access a method of a class, when you access the method, you can access that method's underscore underscore globals underscore underscore, which is going to give you access to all of the variables in the global scope, which will include things like module import. So, like if you do import OS or something like that. So, in this case, where the whole attack happens, is the sub process p open. When shell is true and on Windows, there are almost certainly other areas where you're going to have a similar sort of attack that can happen. This is just the one they called out, and I ran with it because it's easier to let somebody else do the work. Um, it will use the os.environs of the environment, and it'll read. Effectively, it's reading the shell, what shell to use from the environment. So you can
For that
use.
part, would you
Oh,
just be able to hide the Spot the Vuln overlay? It does cover like part of the code there, so it might be a bit tough to read
oh,
for people who are watching.
yeah, for people watching. Hopefully I don't forget to turn this back on, but yeah. Got the sub process you open. Um, Effectively, what ends up happening is you can navigate your way through the classes, through the base classes, and get your way into globals. Get your way into like the sub process, OS, and then its import of OS, its environment. Update the environment variable using the just set attra. You can make your way there, update the environment to read some other shell value. So now when subprocess popen runs, it's going to run with whatever your shell. Well, more than just your shell, it actually has like string there. So basically, you get your own command. Whatever you want to run will run. So kind of a roundabout way of doing it. The core issue to notice here is just that this merge, which isn't really a Pythonic way of doing things. But similar code is out there. I've never really looked for this sort of vulnerability with just or never taken a ton of note about this sort of issue. Um a lot of time if you can't go through nested things, you're going to have a lot less to work with also. Um yeah, I thought it was a really cool idea for an attack here that maybe there's been something reported on in the past. I mean, I don't think the idea has been explored a ton yet. So yeah, I saw it, thought it was kind of cool. Um, Code looks fairly benign, but yeah, that simple aspect of being able to set attributes of a class, uh, basically under your control, arbitrary attributes, can lead to and execution in this case.
Yeah, you can end up chaining it together, sort of like a primitive style, and just keep going until you can get something useful. So, yeah, it was a
Yeah,
cool
and
post.
it reminds me a lot of like the old Python jail CTF challenges, where you have to navigate what's built into the classes and find your way around until you get to well, some sort of jail escape where they like remove access to anything you'd actually want to run code. So yeah, it reminds me a bit about that. A cool issue though. I mean, and the class pollution idea of modifying other classes and having them get reused later is also a very valid kind of attack that I'm not really focusing on that aspect with this one, but yeah, I don't have
Yeah,
much more to add.
of course, it was a bit spoiled if you watched yesterday's episode, as he gave like a little bit of a warning at the topic. But yeah, it's still kind of a cool thing to look for and be mindful of. All right, so we'll jump into our topics. First, for which we have us an active post on a hypervisor bug in FreeBSD's Bhyve, which we've talked about a few times before. In this case, the bug was in the E8 2545 gigabit Ethernet controller emulator's transmit function. A bit of a mouthful. So first, bit of background. Transmit will, of course, send off packets, and in doing so, we'll iterate this ring buffer containing packet descriptors and write out IO vects and such. And there's a few different types of packet descriptors you can have. Context data and legacy data descriptors. Context encodes info such as the header and payload lengths, checksum offsets, things like that. And the data contains a pointer to the physical address of the data buffer. Legacy data, they mention that it's there, but it's not really important, so they don't really go into it in the post. What is important, though, is that the transmit has to handle both TCP and non TCP packets, such as UDP. And any packet can specify TCP segmentation offload, or TSO, if that's enabled. If TSO is enabled, the packet header length is fetched from the context descriptor. And in the case of TCP packets, that is actually properly validated. So I'll just scroll down to the code for those who can see. So you can see on this line, I can't seem to do the highlight. Maybe Z can do it for me, but they check the checksum offset and make sure it's within bounds of the header length. But in the case of non-TCP packets, that checksum offset isn't checked. Only the start address is checked, probably because the top path is the more common path. It's not really common. You're going to be using a like a TCP checksum offset in like UDP packets or whatever. So that check was just missed there. So that can lead to out of bounds read write on the stack, a read when the pseudo header checksum is backed up, and a write when it goes to carry the checksum over. Ultimately, what this gives you is the ability to write 2 bytes at an arbitrary offset up to 255. The offset is only 8 bits wide, so that's why that restriction is there. So it was a bit of a tricky exploit scenario because they go through the stack layout. They have like a diagram on it, and those who are watching can see the like saved instruction pointer is going to be beyond where you can write to. It's going to be beyond that 255 offset. So it was a bit tricky to figure out how to do it. However, the pointer to the header itself can be corrupted, which is used later on for transmitting the packet data. It's used in like 2 iteration loops. So by smashing the header with the out of bounds write, they were able to shift that pointer, leak some stack contents, though funnily enough, while they do demonstrate that, it seems that wasn't even necessary because ASLR wasn't enabled by default on FreeBSD 13's Bhyve, so that's a bit of a meme. For corruption, they targeted a second iteration loop, which would update the IP headers using that header pointer, and as such, they were able to escalate to a more useful relative write of a D word, which they could then use to smash the return address and ROP. ROPing presented its own set of problems, though. They couldn't just corrupt the save frame pointer and make it point to the ROP chain inside the header buffer because the calling function doesn't return. So they basically used their write primitive multiple times to build up a small ROP chain that would pivot the stack to the header, which would then continue the chain to call system. So they kind of have a diagram showing what that looks like. Um, but it's a fairly straightforward pivot. There's nothing too crazy going on there. Still, though, pretty cool exploit, and they were able to make it work despite the initial limitations. Again, hammering home that point that we like to talk about a lot, taking your primitives and upgrading them to more useful ones. That's pretty much what happened here. They had to upgrade their corruption logic a few times, and eventually they were able to call system.
Yeah, it's a
Um,
fun exploit chain. Just going from that pretty small out of bounds, right?
yeah. Now, one thing that is worth noting, they pointed out at the bottom of the post, at least out of the box, this exploit won't bypass the Capsicum sandbox. Though I'm not entirely certain how much that's used. I'm not really familiar with it, but they do point that out at the bottom of the post, so I thought I'd call it out. But um, yeah, I think the reason it wouldn't work as it's written is just because they filter syscalls. So like execve and such wouldn't be able to be called. That said, there is probably it probably could be bypassed fairly easily. They actually reference a frac paper to bypass the Capsicum sandbox, so it's probably not a big deal. But yeah, they do call it out.
How
But
familiar are you
overall,
with Capsicum?
not really at all, to be
Oh,
honest.
okay.
I've
I
not
was just
really ran into situations where I've had to worry about it.
going to ask if it kind of works in line with like SecConf or something, with where it's just doing the filtering, or if there's more to it than that. I mean, filtering
Yeah,
can be a pretty effective sandboxing tool. If you're able to get limited to just everything your application needs. Like, I mean, sometimes applications need quite a bit and you can get away with it, but it's a pretty effective attack surface limiter.
yeah. Yeah, I don't know if it uses something like eBPF or anything like or BPF or anything like that internally. Kind of like the first iterations of SecComp did. It's a bit of an interesting question, but unfortunately, yeah, I'm not too familiar with it, so can't
Well,
answer it.
yeah, I mean, you won't be able to answer, but I more meant just the high level of what it's doing rather than the specific implementation of it using like BPF or whatever. But yeah, I
Yeah,
mean, besides the point.
yeah. So kind of a cool bug. And it's in a bit of a weird area with the E8 2545 emulator. It seems like a lot of these hypervisor escapes are in those kind of obscure components. Um,
A lot of
but
bugs and obscure components, just in general.
yeah, kind of the less traveled road philosophy there. So yeah, not too surprising where the bug was. Like I said, I think it's just a case that it wasn't caught because it's not a common control flow that's going to be hit. But if you're reading the code and you're doing an audit, it's something you'd pick up on pretty quickly. So yeah, cool vulnerability overall, and a good post by Synactive as always. All right, so we'll get into our next post here, which is by Exodus on a Linux kernel bug in Netfilter. And this was posted last month, just before we went on break. Though the bug is a little bit older, there were some previous write ups on it that they link off to that we didn't cover previously. For the most part, this post focuses on exploitation and not so much the vuln. They just kind of give a brief excerpt of it and recommend checking out the other posts for context of the vuln. But effectively, the vulnerability is a lifetime issue with Netfilter sets that don't have this NFT expression stateful flag set, such as lookup expressions. The problem is that lookup and dyn set expressions contain a reference to another set for performing the lookups and updating respectively. And when those lookups or dyn set expressions are allocated, references to those objects are added in the bindings of the reference set. Um, but if the expression associated to the set doesn't have stateful set, it interprets it as like an invalid expression. It'll abort and destroy it, which is a problem because the reference set binding list isn't actually updated to remove that reference. So you have the dangling reference in there, and a UAF occurs whenever that list has to be updated again. So like adding or removing an item or whatever. So they go on to detail some of the objects that are involved, including like the set
Just
expression
before you
lookup and
go
dyn
on,
set.
I want to
Yep.
comment just on the vulnerability itself. It's one of those cases where, if you're looking at things, that seems like the not necessarily the root cause, but part of the issue is just that early return putting into a situation it's not going to expect. I didn't go and look at the code here, but my guess is that they're probably using like just their standard freeing routine as soon as this error happens. Um, so the error happens, does the early return, it goes to a standard free routine for the object, which is going to look and see like, oh, it doesn't have this flag set or whatever, therefore this thing wouldn't happen. Although because of the fact that it's kind of in this non-traditional path, kind of have it. So it's another one of those cases, or at least seems to be one of those cases where that early return is where you end up having the issue start from. Um, Odds are, had it been able to finish, would have set things up more properly, I guess, and then been able to track it. I didn't completely dig into the code on that, so I might be a little bit off base, but kind of want to call it that as more of the takeaway from it, because unless you're doing like Linux kernel work, this specific case isn't something. But in general, those early returns are rife for problems.
Yeah, and along the lines of like looking into the code, the Netfilter subsystem is also like its own beast. It's a pretty
Yeah,
large
true.
subsystem and complicated. And yeah, Malik, I saw your joke from chat. All these non-fungible token issues. It's hard to not think about that when you see the NFT prefix on these like objects and stuff.
We missed the opportunity to get in on the crypto hype in our title.
I know. We'll have to remedy that for the video. But anyway, so yeah, they go into some of the details on the objects that are involved. All the specific like offsets and whatnot. What's mainly important though is the fact that certain offsets are going to be useful to you for where the linked list is updated and where that dangling pointer is going to be. So yeah, that's there if you want to read it, but I'm mostly going to skip over it here. Um, so yeah, but basically what happens is when the binding list is updated, the pointer to a node in the doubly linked list of the binding can end up being written into a freed object, which is quite a useful primitive. Depending on the type of expression, you also have a bit of control on where you want to write. So on kernel version 5.18, which is what they're targeting here, with a lookup expression, you could write the address in 24 bytes into the freed object or 32 bytes, which is how the next and previous line up. And with a dying set expression, you could hit offset 64 or 72. Um, what's notable here, though, and like the central premise of why they did this blog post, is these netfilter objects expressions are allocated using the GFP kernel account flag in 5.18, and in kernel versions 5.15 and up, GFP kernel account allocations end up in their own slab caches, the kmalloc-cg cache. So in 5.15 and lower, where it's a GFP kernel allocation, this bug is a little bit easier in a way to exploit, where it's in the generic cache, and the more common like heat spray primitives like add key are viable. In 5.18.1, though, it's a little bit more work, though it also has a saving grace, which I'll get into in a second. So yeah, ultimately here they wanted to target the kmalloc-cg 64 cache, and further strategy, there's three objects that are of primary interest here. The first of which is FD table, which they found was also allocated in kmalloc-cg 64, and has a pointer to the open FDs table at offset 24, which is useful because they can get a partial free by writing something in there and getting it freed on the destruction of the FD table. And you can control the lifetime of that pretty well through the use of processes.
Yeah, and I
Um,
thought the partial free was an interesting part of this exploit. Just the idea of freeing or basically having that pointer, like using the UAF right, having that pointer be written into something else, getting that freed, so then it frees the pointer belonging to something else. So partially freeing a pointer in a larger object. Um, it's not a novel technique by any means, but I don't think we've actually seen it used in any of the exploits we previously covered. So I kind of just want to call that out as something to think about when you're thinking about exploit strategies.
For sure, it's a cool way to abuse UAF that you don't see super often. So yeah, it's definitely worth calling out.
Yeah, I mean it feels almost like a UAF pivot, kind of.
Yeah. So yeah, getting into the saving grace, the other thing that's allocated in the kmalloc-cg cache is message. So on kernel version 5.14, message allocations were moved from generic kernel allocations to kernel account, which is also in the kmalloc-cg cache. And if message might sound familiar to you, that's because it's a very useful exploitation object for both info leaking and getting a write primitive, which is probably why it was moved to this cache in the first place. But yeah, it's very useful because with message send and receive, it's pretty good for getting like arbitrary read write or info leak or anything like that. It's a very good primitive farm. So yeah, it was kind of neat that they were able to use that here. The final object that they utilized was the time namespace object, and that was just because it contained an operations table and it was interesting for leaking kernel text pointers. So yeah, after they detail those objects, they go into their kind of three stages. So they have a heap info leak, a kernel text info leak, and then finally code execution. Leaking a heap pointer was fairly straightforward. They basically just trigger a UAF on the dyn set object, overlap a message, and then get a set expression object written into the overlap message data, which they can then read back out the message and info leak a pointer to the set object. So fairly straightforward there. The kernel text pointer leak gets a little bit insane, and it was pretty difficult to follow, to be honest. So I'll do my best here. But basically, they weren't able to leak kernel text pointers with their initial leak because the operations pointer for like the set expression would fall into the message header, which you can't read out. So they had to get a bit creative with how they leaked a text pointer. And that's where the FD table comes into play. So they basically duplicate a bunch of file descriptors to get an FD table allocated, trigger the UAF on the lookup object, and then fork a bunch of times to spray FD tables and get it to replace the lookup object. They then create a set with an embedded dyn set bound to the target set, get it freed, trigger another UAF, and subsequently that pointer gets written into the overlapped FD table's open FDs pointer, gets them the partial free on message, which then allows them to sneak in a time namespace object and be able to leak its operations table and get a kernel text pointer. That gets them to defeat ASLR, and then from there it's a matter of getting code exec, which they do a partial free on the NFC set object and fake its operation table to hijack code exec. From there, it was pretty standard. They just do the mod probe path trick, do a short ROP chain to overwrite mod probe path to get root. So yeah, the way they leaked the kernel text pointer was pretty insane, and they do a lot of steps here. I would be curious on the reliability of this chain. It does seem to involve triggering a good number of use after freeze. Now that doesn't necessarily mean the stability would be terrible, but um, you know, it's more points of failure. Now, the other thing worth mentioning is this is in the kmalloc-cg cache, which I'm not actually certain of the stats, but I'm guessing it's probably not used as much as a generic cache, even though it's a 64 byte cache, which is pretty small. It's probably not super active to the point where stability would be a big problem. And with enough heap grooming, you could probably chain the UAF in a somewhat stable way, but still you do have a lot of potential failure points, so I would be curious on the reliability. I don't think they really comment on that.
Yeah, I mean,
um
so talking about the activity in there, um, I believe that's being used. So basically, they've split it up in terms of like the K mem accounting. Um, that being things going in. Well, part of things going in. Are those that need to be accounted, so like more untrusted allocations. So it should still be used a fair bit. It's just kind of splitting up who triggered them a little bit, to make it a little bit harder for allocations coming from like untrusted user or user space allocations versus the kernels created allocations. Splitting those up a little bit is kind of the goal with that. Or at least that's why I understand it. I'm not super familiar with why the change was made, but that's how I understand what happened to be. So like it would still, or it could still have a fair bit of use. I guess depending on what else is going on the system at the time, because that is game more of the untrusted stuff.
yeah. So, like I said, overall, a bit of a complex chain. It is a bit of a tough read, but if you are interested, there is this blog post, and there's also a few other ones that they link to, which I think do a better job of explaining the vulnerability if that's more what you're interested in. Because yeah, theory did one, and NCC Group did one as well, and I think there was another independent one that they don't link to here, but you can find pretty easily by just searching for the CVE. We'll probably add those as like reference links in our show notes, but yeah, there's a lot of information on this bug. It is a bit of an interesting bug and certainly an interesting exploit chain. Um, but because of the like implications tied to the kernel versions, it's not going to be super portable. There's a lot of like allocator changes between like 5.10 and 5.18. Um, both in terms of how the Netfilter table objects are allocated and just with kernel how kernel account works in general. So yeah, it's not going to be super portable, but it is a cool technique, and that's actually why they did this post. Is because those previous posts targeted the lower kernel versions. They didn't really have to deal with, um, the kmalloc-cg stuff, but they wanted to go ahead and tackle that. So definitely some information you can take away there when it comes to the kernel accounting stuff, and some tricks that are probably going to be useful.
Yeah, and
Um,
one of the things that I kind of want to call out on this post is I've had some discussions lately, about getting into modern exploit dev. And I mean, we've talked about this a ton, so I don't want to spend a lot of time on like actually doing so. But I did think that this write up kind of illustrated a key thing where early on when you're learning about exploit dev, you spend a lot of time where it's like you're reaching up to like learning about ROP chains, and then things kind of get a lot more spread out. There aren't as many concise resources, a clear path, whatever. Thing is we're talking about this exploit and like the path to exploitation here. Might have noticed ROP was the one thing we actually completely glossed over. As Spectre got to it, it's just like, and they got their or what was it? Like after they did the ops table, yeah, they got the RIP control and did a ROP chain. And we're like not even talking about anything about the ROP chain because it doesn't matter. Like it's a background noise at this level. It's what's interesting is everything before that. Um and I felt like this post kind of highlighted that by having so much of it just about everything else. And the ROP is not as important. What it starts off with just those early couple basic write primitives, um the 8 byte writes that they've got there, write of addresses. I forget exactly where it is in here, but
yeah, through the linked list. Yeah.
yeah, the link listing. I was just going to pull up the exact primitives they had. Doesn't really matter if you're listening, but just this 8 byte write of an address at this offset. Or these offsets, because they technically have several options there. And it's just starting from there and thinking about what you can reach and where you can go. That's where modern exploitation is thinking about those things rather than thinking about or learning about all these different techniques to get control flow, like keep exploitation or whatever. Like those things matter, and ROP matters. Like obviously you need to know ROP. You need to be aware of some of these other known techniques, like when you've got a heap corruption, go kind of that route or whatever. But a lot of it is this level of primitive work rather than learning more techniques.
Yeah, this post
Anyway,
is a great
that's
example of what like modern exploitation looks like. So
yeah, and it's fairly straightforward in this case. It's nothing too crazy. Like, yeah, it is some Linux internals, but like the starter corruption here, it's a linked list. It's a doubly linked list. It's not I mean, the kernel does it a little bit different than like what you might get in like a university class about a linked list structure, but like it's a linked list. Doesn't get that complicated.
yeah, it's still
But
fairly
yeah,
accessible.
that was one aspect that I think really stood out to me about this post. I mean, we've had others that also kind of go similar, but I don't know. Maybe it was just because of my recent discussions about it too that it was in mind. But yeah,
All right, so we'll get into our last topic here, which is a post by NCC Group on a Stack Overflow and TP-Link's TDP server for their mesh Wi-Fi technology, which, as you would expect, processes TDP packet objects and such. So I'll let Z get into this one. And yeah, go ahead, Z.
Yeah, and I'll say this one was a fairly long post, and I feel like it was just too long for what the actual issue was. In fairness to them, they go into a lot of the details, and they're very detailed about things. There's a lot of background here. There's a lot of exactly what was going on. Of course, we're on audio, so I'm not going to go over absolutely everything here. It is worth noting that this is an ARM 32-bit chip, Little Indian, not an x86, is a little bit more common for stuff we cover. Um, the issue itself, as it was in this process pro packet, there were two flows of reaching that function. One was either you send a pro packet to the server fork, um, or you receive a broadcast request or a broadcast request from the broadcast fork, broadcast server, or process, whatever. And you respond to that with the probe response. Either way, both of them get you send the packet and it gets processed by this process probe packet. And what that does is they have a C library, CJSON, for parsing JSON. So you send a JSON and you're going to parse it in C. What could go wrong? So what they end up doing is, or four vulnerabilities introduced with this, one mesh support version array, which is just an array of values being sent in there. And the vulnerable code, just looking for it here. Effectively, all it's doing is it's reading that value, or reads the size of it first, gets the size of it, and then just iterates. So grabs the size, stores it, iterates over it, setting I, and then it gets the array items indexed by I and just gets that, ultimately leading to it just setting on this shared memory client value, which is a stack allocated, one mesh support version, just allocating in at I. Problem is, even though it grabs the size, it never validates the size. It never makes sure it actually has space to store this. So you can just provide as many numbers as you want. There are some other constraints, but provide many more numbers and just go ahead and overwrite the stack. It's a very straightforward issue, just basically writing without checking bounds, and you have complete control over what's being written at each index. It's just taking whatever value it actually read, the JSON number value. It does validate the formatting a bit. It does make sure it's a JSON number. Takes that number, converts it into a 8-bit int, unsigned int, writes it over. So full control over that data. Um, Exploiting it gets a little bit more tricky because they do end up corrupting a lot of other data. Actually do end up corrupting as they go out of bounds. They end up writing on the array size. They end up writing on some pointers. Basically, like, the actual overwrite gets to be a little bit of a mess. They have to deal with having correct values, because if you want to overwrite the saved return address, you've got to survive long enough to return. If you crash before the return happens, you're not getting your return address executed, or, well, ROP chain. But what they found, the heap was fairly simple. This was Musil, so actually, Spectre, I think you have some experience with Musil and like the heap, with the whole implementation there, don't you?
Yeah, I've worked with Muscle a little bit. I didn't really mess with the allocator very much because I didn't have much of a need to. I was
Okay,
focused more on like the glue between the kernel and Muscle, but
fair, yeah. I
yeah,
remember you
it
had
is a
that
fairly
project a
straightforward
while back.
allocator. Yeah.
Uh,
Yeah, go
yeah,
ahead.
I'll keep going though. I mean, I didn't have anything to really ask you about with it. But yeah, fairly straightforward allocator, fairly simple, and they found it was rather deterministic. One of the things they found was that if they just gave it a nice big spray, um, right here, yeah, they would have their data, their statement. We can guarantee that our data will hit the static address of the 0x2020-200 when we spray um hex 2 million
A bunch
bytes of
of
data.
data.
Yeah, when they
Yeah.
spray a bunch of data, it really reminded me of some of the old school heap sprays, where heap spraying was just about getting the heap into that consistent state, by sending a ton of data and then like it's just going to be consistent after a certain point. Like a lot of allocators now aren't quite as easy to work with. I mean, when you're stuck on 32 bits, you're pretty limited in terms of where the stack can go to. Um, and so it has to be able to grow into this space. So either way, they basically ended up with that as being a consistent thing. But they did take it a little bit further. They did this whole virtualized heap where because this is so deterministic, um, they were able to track exactly where like all their allocations would land and use that to craft all the pointers that they need to overwrite for their actual exploit and tracking like the current state of everything. So they were able to get all the pointers, but effectively once you have that stack overflow, they do just, fill in all the pointers as they need to be using this deterministic stack. Um and all just leading to a ROP chain that they were able to write.
So they do like it is a bit of a multi-stage process there. Basically, what they hit is the support version array pointer that's on the stack. Because one of the problems they had was the support version array pointer was used to iterate through that array where they had the overflow, and they would end up inevitably corrupting it with their linear overflow. So they had to pivot. So they did a bit of a pivot to get their ROP chain going, but it's kind of a minor obstacle. The end goal is the same. There was also some other like considerations they had. For example, those array elements, they were being casted to like a uint8, so just like a byte. But it was a D word, and they only had hex 400. Like the payload max size was hex 400 bytes, so they were a little bit limited on how much data they could get into an overflow there too. But by pivoting into the objects they were spraying, they were able to subvert a lot of those limitations. I thought their virtual peep thing that they did with the simulating the heap, I thought that was pretty cool actually. Um, it's not something I've really seen done with this kind of exploit before, like using that tooling in assistance with exploiting it, but it's a cool idea.
It feels
Um,
like something that's very prone to own centric. Like it feels
yeah,
unrealistic because it basically depends on they call this out as one of their limitations. Like if the mesh link is being used, it throws off all their um allocations and stuff and offsets. So if somebody is using the device you're trying to compromise, so like in a real world scenario, presumably they're not going about doing that, but in a real world scenario, it's probably being used. Why else would it be there? So like maybe you could time it at late at night or something, but like that's a pretty big consideration, but it's good enough for Pwn to own.
yeah. There's a few other tricks they used here too, like to avoid noise on the kernel heap, or sorry, not the kernel heap. To avoid noise on the heap of the servers, they would actually crash one of them. They would intentionally crash the broadcast request process to make the heap grooming more stable and such. They also had to figure out some alignment issues, and there were a few other obstacles. The final point I want to talk about is the reliability. It was pretty shaky overall. Even with the vheap stuff they were doing, um, it was about 50-50 and took 6.5 minutes to exploit because, like Z commented on earlier, they had to spray a ton of data by basically bombarding the router with packets. And it would take about 6.5 minutes to sufficiently saturate the heap to get it into a state they needed, which is a fairly long time. It's not totally impractical, but for Pwn to own, they have a 5 minute limit on your exploit attempt, and you only get 3 exploit attempts. So they talk about that a little bit towards the end of the post. They go into a bit of a hypothetical because unfortunately the Vuln that was intended to be used for Pondo in Toronto, but TP-Link pushed out a firmware update a few days before the competition went live, and it wasn't eligible anymore. So they kind of got burned on that. They do speculate though on if it would have worked going into Pondo own with those constraints. Um, because yeah, obviously, with a 5 minute time limit, they couldn't run for their full 6.5 minutes for their ideal heap state. They have to cut it short, which cut the reliability down to about 35%. Um, but given the fact that they have 3 chances, statistically it should have been able to hit, though it's far from a guarantee. Law of probabilities. It's totally possible that it just wouldn't have hit anyway. So reliability is a bit shaky with it. But it could have worked out. It wasn't totally infeasible. So, yeah, it was a bit of a interesting exploit chain, especially for what's a fairly straightforward Stack Overflow vulnerability. The way they exploited it, they had a few clever tricks there, and the control flow was pretty interesting. So yeah, I like the post.
You mentioned something I didn't actually take notice of. That is,
Yep,
they said the patch happened, they released 1.13 a few days prior to the competition. Fair, that happens for Pwned. Therefore, this vulnerability was no longer eligible. I didn't take note of that word eligible. That's an interesting choice of words.
I thought so too.
Because it's they don't say it was patched. They don't say it was fixed, just not eligible anymore. So like did they change the scope of the contest? I mean, you can't change the scope of the contest with the firmware, so maybe it was like no longer hittable or something like
That's what
that.
I
I don't know.
assume was the case. Was that there was some kind of change that indirectly impacted their ability to reach the vuln. Um, because yeah, like you said, like they do call out a patch was made for the specific bug. But yeah, that term eligible is kind of interesting. Um,
Yeah,
in terms
Rudimal
of like how it's worded.
mentions I think they mean it was too much work to update it, but I don't know if that's the case here. They could say we didn't want to update it or something. Saying it was no longer eligible is just a really weird choice of terms there. Because like eligibility isn't I don't want to do work and it's not patch, it's something else. I don't know. We don't have the information for it, but I didn't notice that before, so yeah, weird.
Yeah. Um, but yeah, I think there's a few things you could take away from this post. I think they did go into a little bit too much detail on the specifics of the heap state and like the alignment and everything. It is relevant, of course, for their exploit, but it's unless you're intimately familiar with like TP-Link's TDpServer, you're probably not going to be able to appreciate those aspects of the post very much. But still, there is a lot of helpful diagrams and stuff, so it's still you can still follow it pretty well. Um, but yeah, it seems like an interesting target. They do call out it's been a interesting target to hit in the past. There's been a few past vulnerabilities that were exploited there. So yeah, I mean, could be an area you could look at exploiting, and there's some good background info in the post as well, and like the architecture and stuff. So yeah, a lot of information there. So that's all of the full topics that we have for the episode. We do have a few shout outs to get into. So those of you that follow around on Twitter might have saw this post being shared around by Saramar. He did a memory safety blog post, which does like a survey of security mitigations and stuff. A lot of the stuff that's talked about in here we have commented on before. For example, Cheery, we talked about a little bit about a couple years ago. MTE is something we've talked about quite a bit, um, as well as like some of the sandboxing work and KALLR type. So we didn't want to do a full coverage on it because a lot of it is just kind of like summarizing what we've already seen. But for those who aren't like intimately familiar with like the landscape and where mitigations have been going, I think this is an awesome post for summarizing things and getting an idea of what different targets look like in terms of how hard they are to exploit. So did want to give it a shout. There are a few things here
Definitely.
we haven't talked about too, like I don't think we talked a lot about data pack, although that kind of ties into chaotic type. But
Yeah, data pack is the KLO type where it does that where every allocation gets assigned like a prefix they're using a few bits or something. I might be misremembering it with something else, but it's part of that KLO type. It's kind of the genericized thing of the signature that it uses, so you can't so you can't get a overlay the UAF or something.
yeah,
I
but yeah,
I know
there
I
are a few
explained that
other.
poorly. Sorry. Yeah, we haven't talked about like auto slab, like GR security stuff, and fire bloom here. Like, there's definitely things we haven't talked about, but um, there's also a lot that we have. Really interesting posts. Like, I like these survey posts actually. Just in general, when we have these surveys of whatever, they're always able to pull out some interesting information, and it's just nice to have a single source to go look at and get this huge knowledge dump.
Exactly. Yeah. If somebody asks, like, "Hey, what are some of the mitigations that are coming in, or something about a particular target?" This is something that you can link to and just be like, "Here, check this out." A lot of good information. So yeah, it's a really good resource in that respect. Some of the other things that are talked about in there towards the end are just trying to avoid creating memory safety issues in the first place by using safer languages like Rust and whatnot. Um, which we've talked about a little bit before on the side. We might do like a more in-depth discussion on that, because it is, a good like first line of defense. You know you can do all the mitigations you want in the world, but preventing memory safety issues in the first place is going to do a lot. So yeah, yeah, just a lot of good things in this post. I would recommend checking it out, even if you're familiar with a lot of these mitigations. Just as a refresher, I think this post can offer a lot of value as well. So definitely wanted to give it a quick shout out. We also have another shout out of abusing RCU callbacks with the UAF read to defeat KASLR. This is specific to the Linux kernel, and is only like super useful when you have certain types of UAF when abusing read copy update or RCU. Because it's so like hyper specific, we didn't want to do full coverage on it, and it is like a technique. There's no like specific vulnerability, and it's not really a novel technique, so that's why we're giving it as a shout out. But if you are doing like Linux kernel exploitation, uh, this could be something good to keep in mind. Just another technique to possibly defeat KSLR when you need to. So yeah, wanted to give that a shout out, but not too much more to cover there. If exploiting kernel use after freeze is something you're interested in, then check it out. Yeah. So unless you have any last minute thoughts, C, we'll go ahead and wrap up the episode.
Yeah, no more shout outs.
All right, cool. So as always, thank you everyone who tuned in. You can catch the VOD on Twitch immediately or on other platforms like YouTube tomorrow. We also have previous podcasts up on Spotify, Apple Podcasts, and more links on Anchor. Feel free to join the Discord and follow us on Twitter. Links for those are down below or in the chat. We like to have discussions there, and that's also where the Spot the Vuln stuff happens. So if that's something you like to do, we have the channel for that. And yeah, we hope you enjoyed the episode, and we'll see you next week.